Hello everybody, hope you're doing well. My name is Mahmoud Yasser and welcome to the new chapter of electrical circuit. So at this chapter, we are going to talk about the parallel circuit. If you guys remember, last chapter we were talking about the series circuits and they have a main concept. It means that all of these components are connected side by side and the current goes through one component is the same as another one and totally as the same as total current. So we had a little bit of problem with those kind of circuits. Despite of the fact that they were good, but it had an issue. And that issue was about the fact that those guys cannot handle only one smaller teeny tiny problem with one of the components. If something happened to any component like resistor, like some kind of diode, everything would be collapsed, everything would be disconnected. Imagine that you are using the Christmas lights and after that one of those bulbs are going to be broken. What would happen? Everything is shutting down. So how we can fix it? We are going to talk about a new concept of electrical circuit that we call it as parallel circuit. We'll see that this guy is going to solve a couple of issues for us and obviously it has a couple of problems, but eventually we're going to use that by itself or maybe in some kind of beside a series circuit. So without further ado, let's just talk about it. So as I just told you, this chapter we are going to talk about the parallel circuits, and at this point we are talking about the fact that components are going to share the power of parallel circuits. Imagine that I do have a case that all of the lights are connected in series. So at this point, I do have the series configuration, which is old-fashioned. Why? Because it just have the single path of failure. If something happened to one of the lights, everything is going to shut down. So in order to solve that, I have another solution. That solution is about a parallel configuration. It means that there are multiple independent paths, and I will talk about it how. So let's see. The first some kind of diagram is about the series circuit. As we were just talking about it, everything is connected side by side to each other with one wire at a time, and then all of them are connected to your voltage source. So at this point, the current that goes this way, or I total, is equals I1 equals to I2 and equals to I3. But as I just told you, we do have one main issue, and if anything happened to one of your components, everything is going to collapse. In order to solve this issue, we do have a multipath thing. It means that right now, instead of just connecting side by side, we are going to connect them two legs by two legs, or two common points. So at this point, I know that for a fact that the VT, we can call this ET, doesn't matter, is going to be equal to V1, V2, and V3. Right now, they're sharing the voltage. All of them would be the same. But what would be different on the previous part that we had current would be the same for all of them. At this point, when I do have I total, this guy is I1, this guy is I2, and this guy is I3. We do have the current based on the resistor. So based on the KCL, we know I total equals I1 plus I2 plus I3. As simple as that. So if you want to give you an example, imagine that you do have your household and everything is wired obviously in parallel, because if something happened to one of your outlets, we don't want anything or other things to just shut down, right? That's why we do have it like this in parallel. And what about the automatic, your some kind of car, your automotive system? It means that the headlights, the radio, and everything is going to be connected to your battery, but in parallel. So the main advantage would be one failure doesn't kill the entire system. So the three golden rules about the parallel circuit. The very first one is that voltage is constant, or the voltage of your source is going to be as the same as voltage of all of those branches. That's why we say ET is equals V1, V2, V3, just like the way that I told you for the second circuit. So next one would be about the currents. As I just told you, currents are the things that are going to be different and based on the resistance. So at this point, in order to find the total current, you have to add them up. It means that currents add up. So this guy is something we call as a Kirchhoff's current law. This says that I total is going to I total, or the current that gets outside of your source is going to be I1 plus I2 plus I3 itself. And finally, what we do have the resistances. Resistances at this point are going to be reciprocal. What does that mean? At the previous point, we had R total is equals to R1 plus R2 plus R3. Simple as that. But at this point, in order to find the total amount of resistance, or RT, we have to use this specific formula. What does it say? It says 1 over RT is equals 1 over R1 plus 1 over R2 plus 1 over R3, or plus whatever component is connected in parallel. Proving this fact that why we do have this formula is very easy. We can use previous rules of the voltages are the same and the currents should be add up, and after that prove this one. It's not necessary, but if you want to do that, I can help you. If you have any question, you can just comment me down below and I can help you how you can prove it, but just try to memorize it. It would be good for you, obviously. So again, remember, parallel circuit, same voltage, current sum, reciprocal, resistance. So let's talk about it. Let's talk about, by the way, this way it should be connected over here. Let's talk about calculating the total resistance again in an example. As we know, 1 over RT is equals 1 over R1 plus 1 over R2 plus 1 over R3. Imagine that I do have a case that there are 3 resistances, 10, 20, and 30. How can I find the total resistance? Easy. 1 over R1 is 1 over 10. 1 over R2, 1 over 20, 1 over 30 is going to be 0.033. So at this point, I do have my final number. It has another name. 1 over resistance is going to be conductance. I will talk about it in a few slides. But it is show you how resistance is somehow eager to let current pass. Because as we know, resistance is the amount of resistive energy that each component has against the movement of electrons or the movement of current itself. So at this point, we do have 1 over RT. Am I done? No, obviously, because I'm looking for RT itself. So I have to find the reciprocal of that. It would be 5.4. So for the sanity check, we have to know something. For the series circuit, if you add all of those resistances together, your final result is going to be bigger than the biggest resistance that you have. In the parallel situation, everything would be vice versa. It means that your final number should be smaller than the smaller resistance that you have. It's some kind of characteristic of adding reciprocals. So at this point, when I do have my number, it is 5.46. I know for a fact that it is right. Why? Because it is less than 10 ohm itself. As you can see, R1, R2, and R3 are like this, but R total is smaller than all of them. So what would happen if I do have only 2 resistances? Either I can find it 1 over RT is 1 over R1 plus 1 over R2, or I can use a shortcut. This shortcut, which would be better to memorize it, is going to help me. Instead of just doing 1 over R1 plus 1 over R2 by itself, I can just follow this formula and still I'm going to have the right answer. For instance, I do have a 12 ohm and I do have 6 ohm. By the way, this guy should be like this. Like that, obviously it would be a problem. We are going to have a short circuit at this point. So at this case, we are going to have something like that. It would be better to redraw it, by the way. So this is going to be the second resistor. Both of them are connected to each other, something like this. Cool. So at this point, if I would like to find the R total, the only thing that I have to do is just follow this path. R1 times R2 divided by R1 plus R2. So at this point, I do have 4 ohm itself. A 4 is going to be less than my smaller number, which is 6, so it is right. Again, remember, this shortcut only works for calculating 2 resistors at a time. 3 resistors? No. Only 2 resistance at a time. So what would happen if rather than just 2 or 3 different resistance, I do have 2 equal resistance? At this point, if I assume that my R1 equals to R2, my R total would be R divided by 2. Imagine that you have 10 and 10, my finally would be 5. Maybe some of you would ask how? Let's do it. 10 multiplied by 10 divided by 10 plus 10. It would be 100 divided by 20. It would be 5 ohm. As simple as that. So we do have some practice over here, and you can just pause the video, think about them, and then just comment me down below. It would be so simple. Again, we do have 2 resistances. Some of them are the same, some of them are not. Try to find the answer and comment me down below. If you have any problem, I will look after that. Don't worry. So let's talk about the current flow, because as I just told you, the one thing that would be different in parallel circuit is the current itself. What does that mean? It means that based on the Ohm's law, we know I is equals V divided by R. And if I assume that my voltage is which is the same, because the voltage of parallel circuit or the parallel source is connected to each of those components. If I increase the R by assuming that the V is going to be the same, actually I'm decreasing down the I. What does that say? It says that current likes or loves the pattern or the path that has the least amount of current. That's why. If you just look at your previous circuit, when we had 3 different resistors side by side or not in parallel, you can see that the side or the path that has the least amount of current has the highest, has the least amount of resistor, has the highest amount of current. And we can see it. It's not completely obvious. So for instance, in the question that we have, that R1 was 10 ohm, R2 was 20, and R3 was 30. Obviously, we can find the current based on V divided by R, right? The very first thing is V divided by R total. We can find the total current, 2.2 amp. For each of those paths, we can find the current based on V divided by R, which would be what? 12 divided by 10 ohm, 1.2. 12 divided 20, 0.6. 12 divided by 30 is going to be 0.4. And as you can see over here, the highest amount of current is for the least amount of resistance itself. And finally, if you add them up, you're still going to have those KCL itself. So let's talk about the rule. Let's talk about the current divider rule. If you guys remember, we had the voltage divider rule, and for voltage divider rule says that if I do have a series circuit like this, and if I do have R1 and if I do have R2, rather than just finding the current, then finding the voltage, I can find the voltage directly for each of those resistances. For instance, VR1 is equals to V total times R1 divided by R1 plus R2. I can do the same thing for the second one. But when I do have the current divider, it would be a little bit different. Everything is somehow the same, but first of all, we are talking about the parallel circuit. Then, if I would like to find the current that I would like for the first resistor, I have to look after the second resistor. So at this point, I1 is same as the current divider. Instead of VT, obviously we have to use IT. And on the denominator is going to be the total resistance. And finally, on the top would be R2. If I would like to find the I2, everything is the same, but on the top would be R1. Maybe for some of you, it would be a little bit hard to memorize that. Say that I really like a formula that is going to connect me to the main resistor. If I would like the I1, give me R1. If I would like I2, give me R2. So we do have another formula for that. That IX, or the current that goes through the path that you have resistance in, is going to be IT, but instead of just RT and denominator, we are going to have it in numerator. It means that RT would be on the top and RX is this resistance that you need. Either you can use this way or this way, doesn't matter, both of them would be the same. So let's see an application. Imagine that I do have a connection, or I do have a circuit that I total is 4 amp, and then I do have my R1 as 10 amp and my R2 at 30 amp. And after that, I would ask you how I can find the I1, or what is the formula for I1. You would say that it's simple. I1 is I total, which is 4 amps, and on the top, I'm going to consider the resistance that I don't like. It would be 30, or R2, divided by R total. If you do that, you do have 30 amp. If I do the same concept for another resistor, I2 as what? 1 amp, which I expected that. Why? Because the path that has the highest amount of resistance has the least amount of current. If you add them up, you're still going to have 4 amp. As simple as that. So let's talk about the conductance. We were talking about the resistance. Again, resistance is the way that you can measure how much resistive fighting or resistive energy does a component has against a path of current or against the movement of current. So we had it as R, which was very obvious, but at some point we do have another concept as conductance. Unlike the R, that if you increase it, your I is going to decrease, conductance means that how much or how some kind of a component is willing to let a current path, how much your component likes the current. So obviously it's going to be reciprocal of resistance, and if you increase the conductance, it means that you're increasing the current movement possibility. And the good thing about conductance is that if you find it for each resistance, instead of just adding the reciprocal of those resistance in order to find the R total, which would be sometimes a little bit pain in the neck, you can find the conductance for each resistor, add them up, still like the way that we did for the series resistance. But remember, at this point we are talking about the conductance, and you can find the final conductance. If question asks to find the final resistance, you can find a reciprocal of that. Reciprocal unit measurement was ohm, but conductance is going to be Siemens. So this is just a name. It's not kind of fancy panting. It's just kind of name. So let's talk about it in detail. So again, definition: conductance, or which showed by G, is the measure of how easily or how well the current flows and current flows. It's opposite of resistance, right? So at this point, when I had 1 over RT is 1 over R1 plus 1 over R2 plus 1 over R3 or any other component in parallel with that, GT is going to be simple, just like the resistance that you had in series. But at this point, we do have reciprocal of that, right? So parallel conductance, we can have add together just like series resistances. This simplifies the concept dramatically, right? Instead of just doing everything, we can do this part. So in our example, imagine we had 10, 20, 30. Instead of just finding a reciprocal at the beginning, we can find the reciprocal of each at the beginning, then add them up. If you add those guys up, your final value is going to be this guy as a conductance. But if you would like to find the R total, you can some kind of find the reciprocal of that. As you can see over here, whenever my R is smaller, my conductance is higher. When the conductance is higher, it means that current would like to pass that way more likely in comparison to others itself. So let's talk about the power. So what does it mean by power? Again, power means that how much energy is going to be dissipated inside each component. Right now, we only have resistance. It means that those guys are going to only consume energy. Whatever energy that your some kind of source is going to produce is going to be accumulation of all of the energies that your resistances or components are going to consume. In the future, we will talk about capacitors and inductors. Actually, those guys can also somehow save the energy and then also pass the energy to you if you need that, right? So let's just talk about it. So at this point, we had a formula that P is equals V times I, P is equals to RI squared, P is equals V to the power 2 divided by R. Again, we would like to find the power over here. For each one, for each branch, we do have the voltage. If we do have the resistor, that will be better to use this one. Maybe some of you will say that I don't like the voltages, so that's okay. So we can find the current and after that find this one. But it doesn't matter. At the end of the day, your P total, the amount of power that your source is going to create, should be as the same as P1, P2, and P3 by adding them up by itself. So let's talk about this question. VT was 12, R1 was 100, R2 was 200, and R3 was 300. Find the power in each branch. V2 divided by R, add them up, this number. Still, you can prove it using the P total is equals V total times IT. I do have the IT. Simple. I had the RT and I can find the IT, and also I do have my the voltage itself, and still should be the same itself. So it is very critical. Again, each of the components that you're dealing with only can handle a specific amount of power. So you cannot expect a component to handle unlimited amount of power. That's why you have to be careful what kind of component you use, especially diodes, because they're so fragile, so on and so forth. So this is going to be step-by-step procedure when you're dealing with your circuits. The very first thing that we have to identify is that all of the components are going to be parallel. That means that they're going to connect it across the same 2 points, right? This is the first step. The second step is about establish the voltage. You have to see at this point, the source voltage is the same across all of the branches. That was the very important characteristic of each parallel circuit. Then you have to calculate the RT. That was simple. Either you can use 1 over RT equals 1 over R1 plus 1 over R2, blah, or you can use the conductance way, right? Both of them, you should have the right and the same number. Calculate the branch current. So at this point, use the Ohm's law in order to find each branch current, which is going to use for that in order to calculate the total current, because we would like to see that the KCL works or not, or use it for our total power. Finally, we have to verify the I total is going to be the same as some kind of addition of all of those currents together, or KCL, and then we can calculate the power. Does it somehow necessarily says that you have to remember these steps? There are some kind of intuitive ways or steps, but still it doesn't that kind of hurt if you have it in your mind. You check everything step by step. Cool. So let's see everything in a table about the series and parallel. As I just told you, the series circuit is like this. Everything is connected side by side. In parallel circuit, everything is like this. They do have 2 points that are common. So for the current, again, they would be constant all the time. IT is equals I1, which equals I2, whatever component that you have. But on another hand, we do have the current is going to be divided in each branch based on the resistance that they have, because we know voltage is the same. Voltage is going to divide among components, is going to add to total, or we have to follow the KVL, or we know fact that we do have the voltage divider formula. Finally, for the currents, for the voltage in parallel circuit, all of them would be the same. In order to find the resistance, it would be easy because R total is R1 plus R2 plus whatever component that I have. But on another hand, we do have it for the parallel is going to be a little bit challenging. 1 over RT is 1 over R1 plus 1 over R2. For the total R, if you increase each of those resistors, the final value is going to increase as well. But in parallel situation, if you increase any of them, your total resistance is going to decrease as well. Effect of open. So as I just told you, circuit is going to fail completely because as we have in the series circuit, everything is connected side by side. If something is going to be open, it means that the current doesn't have any path to flow, so everything would be shut down. But on another hand, we do have the open branch where any of some kind of path in the circuit itself for the parallel one, if something happened to one of the branch, it doesn't mean that other branches would be shut down. They could be a little bit affected because right now they do have more current to share, but still they're going to work. Another thing about the primary use, we are using for the current limiting. I talked about it actually. When you do have a resistor and you have a diode, you would use that. We use it for voltage division. I talked about it. We used it for power distribution for the parallel one, independent device operation, and so on and so forth itself. So let's talk about the real world application. As I just talked about it, the real world application of the parallel circuit is so vast because it doesn't have that specific, that important disadvantage of one path fails, everything would fail, which is talking about the series. At this point, we do have the parallel. If something happened to one pass, all of the passes are going to work. So for the first one, we do have the household wiring, right? All of those outlets are connected to each other, but it doesn't mean that if something fails, other one would fail as well. What about your machine? You do have the 12 volt of battery inside your car, and this 12 volt is going to energize all of your components. But if something happened to one of them, then nothing would happen to all others, and everything was going to work again. And what would happen if you do have two batteries side by side? They are going to help out each other. It means that they're going to produce more amount of current for you, but the voltage is going to be still the same. If one of the batteries dead, or if something happened to one of the batteries, still another battery is there as backup for our work. So let's talk about the troubleshooting. As you just talk about the series circuit, we also do have the troubleshooting in parallel circuit. So what would happen if I do have the open branch? The symptom is this: one device stops working, but others on the same circuit are fine. So total current measured is going to be what is the source is going to decrease. So this is the fact. What would happen at this point, as I just told you, if one of the resistors is going to fail, it means that my total R is going to increase, right? At the same time as V, which is something constant, divided by R total. If my R total increases, my I total is going to decrease as well. So again, the cause is an open circuit in this specific branch. So this is something related to broken wire, broken resistor or anything. The consequences: total resistance on the branch is going to increase, and also all of the current would decrease. So what would happen if you do have a short circuit if one of your resistance in one of those branches, which is a very dangerous thing, because at this point, if you do have the short circuit in one of these resistances, what would happen? It means that your 1R1 plus 1R2 plus 1R3 is going to something happen to that. R2 is going to be 0, something around 0, and everything is going to collapse. It means that I do have only one wire, and current says that, oh my god, I do have only one wire, so I can pass everything through that. So your voltage is going to only be dedicated to this one wire, and it's going to get rid of all of these two. So you are going to have so much current that goes through a wire itself, and your current is so high that it could damage everything after that, right? So we have to have a fuse. That fuse would be activated and everything would be shut down. So again, the symptom over here is that the entire circuit goes dead instantly because the fuse or circuit breaker should activate it. What is the cause? The short circuit in one of the branches, like the second one, third one, doesn't matter. Create a path of near zero resistance, and the consequent is a massive, potentially dangerous surge in total current, which is something that we don't like to have. So, and how is some kind of your meter is going to affect the circuit? In parallel one, it is very important. If you guys remember, we were talking about the voltmeter and ammeter. Voltmeter should be connected in parallel and ammeter should be connected in series. Why? Because voltmeter has a huge amount of total resistance inside, and if you connect it to the resistance itself, actually somehow it can be ignored. Imagine you have 1 mega ohm and make it in parallel with 10 ohm. If you do the calculation, R1 times R2 divided by R1 plus R2, your final resistance is still going to be maybe 11 ohm, so it doesn't have that much of effect. But what would happen if your resistance that you're connecting to your voltmeter is somehow going to have the same amount of resistance inside itself. Imagine that you connect your voltmeter, which was 4 mega ohm inside of that, to another 4 mega ohm resistor. Obviously, your total resistance is going to be 2 mega ohm. But as we just mentioned, we would like the fact that my voltmeter doesn't have any effect on the system. But on the second option, when you do have 2 mega ohm, my some kind of voltmeter sees, some kind of voltage source sees that, oh, something happened to my total resistance. My total resistance is somehow decreased. So I have to inject more amount of current and everything would be collapsed. So at this point, it is very important when you connect your resistance to your voltmeter, make sure that the amount of resistance that you have inside your voltmeter would at least 100 times greater than your resistance itself, right? On another hand, if you do have the ammeter, still ammeter has the very low amount of resistance inside of itself. So most of the time it doesn't have any effect, but at a point that if you do have this kind of small amount of voltage, it's going to affect the whole system. So most of the time when we use the ammeter, we are talking about 10, 12 volts, not talking about maybe 200, 300 millivolts. So you have to use some kind of resistance for that part. So, okay, before we talked about the parallel circuits and series circuit. At this point, we have so much idea that how we can use them and how we can apply them in our day-to-day work. But the main question is that how we should use them in the lab. Just before having that one in the day-to-day, some kind of our devices, first of all, we have to know how we can apply that. So in future slides and future works, we are for sure going to have a lab, some kind of review of how we can do that. We are going to have the simulation. We are going to solve so many questions. Then we are going to into the lab and talk about it, how we can connect all of those guys side by side. So thank you guys for being here with me. Again, if you have any questions, just please comment me down below. I would be more than happy to help you with that. My name is Mahmoud Kiasari. Have a super great day, night, whatever. See you around.